Right. This is where we finished off yesterday. Friday. Okay, so we finished off on Friday. We talked about the bus per control unit. That is the electrical brain for the whole of the aircraft. So again, it's looking after every electrical component in the distribution system of the whole aircraft, apart from the generator control units, which control their own generator. But the GCU always tells the bus power control unit what the state of the output of a generator or if it has failed, because it needs to know. All the things we looked at, we said basic monitors, transformers, load controllers, control switching. We might even control shedding loads. And one of the things we is going to be looking at, okay, again, looking at, not controlling, is, when I get it up and running, come on, give me a little cursor, is a TRU, okay? Now, we talked about that in day one. A TRU is a transformer rectifier unit, okay? Transformer rectifier. It takes the AC supply and converts it into DC, okay? Converts it into, excuse me, converts it into DC. Now, it's a transformer, so the transformer changes the AC from a high value to a lower value due to the ratios between the primary and the secondary coils, the number of turns. So as I said earlier on, I said on Friday, whatever comes in to a TRU, it'll be same proportion ratio comes out because the ratio of the currents doesn't change. So we'll be wanting to keep the input to the primary coil of the TRU constant. So my output will be constant, and that output will be 28 volts. So as you can see down here, gents, here's my input. It doesn't matter what the supply is, but 240 out. There's the primary turns. There's the secondary turns. And again, it's a lower value. You can see there, I've got more turns to less turns in the secondary. So it has to be a step down AC transformer. So that's the transformer part of the TRU. The rectifier bit is this full bridge wave rectifier, okay? That's going to convert my AC into the correct value of DC, okay? As you can see this down here, you've got a DC output. So we said there, TRU converts AC into DC. Here's a block diagram of what you've got in the TRUs you have in your aircraft, okay? Remember now, our AC input is 3 phases, A phase, B phase, and C phase. So each one of those phases has its own primary coil. On top of that, each one of those phases working. Each one of those phases, so that's my primary, and this side is my secondary. It also has 2 secondary coils, okay? One, which is delta, and one, which is star connected. Now, if you go back to your own module 3, star and delta help produces. If I have a star, I can have 2 values of AC, so it's more efficient for AC. Delta, I can have 2 values of current, so it's more efficient for current. But on top of this, each one of those, okay, is going to give us 3 outputs, okay? So I'm going to have 3 outputs coming from here. So we're actually going to get 3 waveforms. Right, so there's first part of A, first part of B, first part of C, and then I'm going to have, okay, the negative side of A, B, and C flipped over. Now, if I was to look at delta, delta shifts everything by 90 degrees. So the actual relationship between star and delta is 90 degrees. So there's my currents now going like this. And you can see now it's starting to smooth out that 28 volts DC. So that's how it's connected. So we're getting that DC there. We're now going to put it through a full bridge wave rectifier, okay? So that's going to give us this DC, and what we end up is a very, 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 very high frequency ripple at 28 volts. So if you were to look at your oscilloscope, if you look at your meter, you just see 28 volts. You'd only see a tiny, tiny ripple if you put it under an oscilloscope. So that's the 2 parts. We've got primary and we've got a secondary, and then we've put it through the full bridge wave rectifier. So that part here is my rectifier part. Don't worry, you're not going to be asked how the primary and secondary produce the ripple. That's just, I'm just giving you a bit of information. But be aware it's a transformer. It transforms, it steps the AC down and then rectifies the AC into DC. Now, got to look at some of the protection side. Okay, we've got to look at some of the protection we have for our TRU. And the first thing is, you think about it, I have a transformer and that's going to be carrying lots of heavy current. Lots of current produces heat, okay? So heat. So all the TRUs I have ever seen all have some sort of cooling system, okay? And this one here, we've got a fan. It's going to blow air across the coils of my TRU. Okay, it's going to blow air across the coils of my TRU, keeping it cool. But you might have a problem with it. Either the primary and secondary coils overheat, or let's say the fan stops, fails, seizes. The heat is going to build up. Okay, the heat in the system is going to build up. So we've got to do overheat protection. Yep, and it's as simple, it could be as simple again as up here with a little bimetallic strip. It heats up, but this time the bend. So normally I've got 28 volts, and in a normal condition, this is open. Okay, so basically nothing gets to my overheat, TRU overheat caption, or either a caption in the cockpit, or again, something to activate a caption on the ECAM or ECAS system. It starts to overheat. Okay, I'll get to the point where it'll eventually bend down, completing the circuit, putting a caption on the cockpit. Okay, putting the caption on the cockpit. Depending on the type of aircraft, that might give, if a pilot sees that, it gives the pilot the option to manually switch it off. And a lot of modern aircraft, the system itself will switch it off. But it doesn't matter, either way, we'll remove the TRU from the system. Okay, we'll remove the power from the TRU. Now let's look at this reverse current cutout protection. Yep. We usually have 2 TRUs per aircraft. If it's a 2-engine aircraft, there'll be 2 TRUs. That means I'll have 2 TRUs onto the DC bus bar. Let's look at what happens if the TRU fails or it shuts down. Okay, let's say the total TRU fails. Okay, total TRU fails. The output for my TRU is going to be 0 volts. But look, I've got 28 volts on my bus bar. Which way is current going to flow? It's going to flow from the bus bar back into that TRU. We can't allow that to happen. So we've got a reverse current cutout device. It could be like the RCCB, or it could be a big blocking diode. Doesn't matter which it is. We've got reverse current cutout protection, and as soon as 1 amp starts to flow from the bus bar back into the TRU, we remove the TRU from the bus bar. Okay, we remove the TRU from the bus bar. So that's 2 conditions, overheat and reverse current. The third one is my voltage protection. And we're going to protect between over voltage and under voltage. Okay? Over voltage, approximately when 33 volts starts to come out of my TRU, I need to shut it down. I really do need to shut it down, putting too much voltage into the DC system. So we will actually remove the supply from the TRU when it gets too high. But we've also got under volts protection, and it's approximately when we get 22 volts coming out. And you can see here now, if I've got 22 coming out the TRU, 28, we're going to end up having reverse current. So again, we will shut down the TRU when the output of the TRU drops below approximately 22 volts. So let's look at the 3 things we're going to protect a TRU for. Overheat, yep, if the fan fails. Over voltage, if the output of the TRU goes above 33 volts. Under voltage, if it goes below 22 volts. And reverse current, to stop the current flowing back from the bus bar into the TRU if the current goes above 1 amp. Okay, so remember the three things we're going to protect the TRU from: overheat, reverse current, under and over voltage. Okay, 3 things we protect the TRU from: overheat, reverse current, and over and under voltage. Okay, all happy on that? Simple. Now we're going to look at... Okay, yes.
Can you explain the reverse current once again?
If I have, okay, let me just clear this. Okay, let's clear it. Normal output, Chris, is 28 volts. Agreed with that? Yeah?
Yeah.
And that's going to connect, that's going to connect to a bus bar, and that's also going to have 28 volts if I have another TRU on it. Agreed? Or it could be the battery bus bar, doesn't matter. What's going to happen if, let's say, the output drops down to 22 volts? Which way does current flow? From a low potential, a high potential, or a high potential to a low potential?
High potential to low potential.
So now If I've got 28 volts on the bus bar and 22 volts coming out of this TRU, which way is current going to flow?
From the bus bar to TRU.
Right, so the current is going in the reverse direction. Agree with that?
Yeah.
So now, if 1 amp flows back into the TRU, the reverse current protection operates and will remove the TRU from the bus bar.
Okay.
Okay, happy in that, Chris?
Yeah.
Yeah, good. There's several ways we can do it, but we don't have to talk about it on this course. That, again, how it would be done would be in a type course. Several different ways we can do it. Next thing we're going to look at is for who we talk. Prakesh, and we asked about the solid state voltage regulator this morning. Was that you, Prakesh?
Yes, yeah.
Yes.
Yeah.
Well, this is what we're going to talk about now. Okay, so we're going to look at a solid state voltage regulator, how it controls high voltage, low voltage, and the correct voltage. Now, from the AC brushless generator we saw on Friday, this is basically a modification of it, okay? There's my voltage regulator, but now rather than being an analog coil, you can see here it's going through amplifier, amplifier, and it's got an exciter field. The exciter field's not changed. What we do with the exciter field is different, okay? So as you can see here, we monitor the output from the generator. We've got this error detector. All the error detector is going to do, it's looking for 115 volts. If it's too low, it will send to the system, you need to get the excitation up. If it's too high, you need to get the excitation down. That's not changed from an analog voltage regulator. That's not changed. All we've got now is this, we're coming into this solid state, the electronics. Okay. So what we're going to look at is how the electronics work, okay, or what the electronics do. We're not going to look at how they work. We're not going to turn transistors on and off. What we're going to do is look at what it does. So here's my excitation field. Yep. And when it was an analog system, if the output voltage was low, my excitation went up. We all agree with that, gentlemen? Yes? And if my output voltage, okay, coming out of the generator was high, my excitation voltage would go down. Now, we're talking electronics. Electronics, with a whole lot of transistors, electronics is on or off. So here I'm going to have, it could be 28 volts DC is my excitation voltage. Other aircraft might be slightly different. But that 28 volts will be there all the time. So I can't increase the excitation voltage up to like 30, 32 volts. And I can't decrease the output voltage to 24, 22 volts to get. So what can I do? Well, the electronics is going to turn the excitation field. It's going to control the excitation field and it's going to turn it on and off. That's what electronics do. They're either on or they're off. So let's look at the three conditions we're going to look at. Okay. If my normal generator voltage is 115 volts AC. It's the voltage we want. Okay. So I could say I have the average or the datum excitation voltage. But if I have a constant DC, okay, what would happen is my voltage would start to go output. If I kept 28 volts on all the time, I get 115, 116, 117, 118, 119, 120, 130. It would keep rising, okay, until it got far too high. If I turned it off constantly, I would get nothing. So when I have my normal output of 115, this excitation field will pulse on and off. And if the generator voltage is correct, get this person in. If the generator output voltage is correct, the time that the excitation field has that voltage, the time the excitation field is on is the same amount of time that is off. So now if I was to look at the average voltage over time, you can see here it is halfway, okay? So I've got the correct average amount of excitation field, okay? If I have the correct amount of average, it means my output is correct, okay? So the excitation field, when I have the correct output from my generator, the excitation field will pulse on and then off, and it will pulse on for the same time that it pulses off, okay? So I'm going to get, if you look at there, the average field, you can see here it's halfway on my excitation current going through the coil. Now let's look at the output of my generator is too low. So let's go back to here. When the output of my generator was low, okay, when the output of the generator is low, I got my excitation up. But now, as I said, we've only got one voltage. So what we're going to do now is we're going to pulse that DC, that voltage, on longer than it is off. So if you look up here, so I've got low generator voltage. I'm going to pulse my output on much more than it is off. Again, there's my on and there's my off. So I'm going to pulse my excitation field on, off, on, off. And if you can see here, the average field now, the field excitation has gone up. So now I've actually produced the excitation voltage is on more. So that allows my output to come up and it drops off a little bit. Then it allows it to come back up again. So output is low, the generator output is low, the excitation field in a solid state will be on longer than it is. So I'm actually getting it up. Now look here again, if my output from a generator is high, in an analog, the excitation voltage would go down. But as I said earlier, this voltage in my solid state is constant. So now if my output of my generator is too high, I'm now going to pulse the excitation field for a small time on and a large time off. Small time on and a large time off. So you can see the average excitation field has gone down. Okay, just like here. So my average excitation field has gone down. Therefore, my generator output has gone down. Okay, so that's what we're actually going to do in a digital voltage regulator. We're not going to physically change the excitation voltage. What we're going to do now is pulse the excitation field. If the voltage is correct, the time on will equal the time off. If the generator voltage is low, the time on is large, the time off is small. If the output of my generator is high, the time on is small and the time off is large. And that is how we control excitation in a digital solid state voltage regulator. Okay, and a digital solid state voltage regulator. Okay, Prakash, you happy with that? Everyone else happy with that?
Hello, yes, Ian, thank you.
Yes, okay. So just remember that all we're doing is getting the average time that the excitation changes. So we're just changing the average time. So again, if it's a low voltage, it's a larger time on. And in the old analog system, if it was a low voltage, it was a larger voltage. So the larger hasn't changed. Okay. So that's how we control excitation in a digital or solid state voltage regulator. Next thing we're going to talk about is something called the point of regulation. Okay, the point of regulation. Now, what is, so we've got the two parts. There's my generator side on the left-hand side of the generator contact breaker. And on the right-hand side is the bus bars or the distribution. And we know that the bus bar has to have an output of 115 volts AC, because all our systems have been designed to work on 115 volts AC. So that's what I must have here, 115 volts AC. Yep. And here's my voltage regulator. It's sampling the voltage just before it goes into the generator contact breaker. Why there? Okay, why there? Well, let's look at the generator itself. So if my generator produces 115 volts AC. Now imagine this is on the port outer wing of a 747 or an A380. So the generator is attached to the outermost engine. And then it has to come all the way down the wing and then all the way into the avionics compartment to where the voltage regulator is. These cables have resistance, okay? And as we now know from basic electrics, if I have resistance, as current goes down it, it's going to produce a voltage drop. Now I can tell you from my last aircraft, so it's a helicopter, from the back of the gearbox to the voltage regulator in the avionics compartment was about, I don't know, 8 or 9 meters, maybe 10 meters at the most. And in that time it could drop nearly 3 volts. So now look at this. If I think about this as a 747, the generator on the outer engine, I might drop 10 volts all the way down that line. So now, rather than having 115 volts, I'm going to have 105 volts. I'll have 105 on my bus bar. But my AC systems need 115. So this is what we call the point of regulation. The voltage regulator, rather than sampling the output of the generator here, we need to take into account of the voltage drop by the resistance of the cables. So that's why we measure the output voltage of the generator just before the generator contact breaker, okay, or what we call upstream from the generator. So just before it goes into the distribution, okay, and that's the point of regulation. So why do we have a point of regulation? It's to take into account voltage drop caused by the cables. Okay, to take into account the voltage drop caused by the cables. Where do we have the point of regulation? Well, the point of regulation is just before the generator contact breaker, before the AC goes to the distribution, i.e. the bus bar. Okay, so two things: point of regulation. Why do we have it? It's to take into account the voltage drop caused by the cables going from the generator to the bus bar. Where do we do this point of regulation? We do it just before the generator contact breaker. Okay. And those who are B2s, you'll sometimes see the generator test point is just beside the generator contact breaker. So if you've got to do sampling, it's usually there. So, any questions on the point of regulation? No. Good. As close to the bus bar as possible, but between the generator and the contact breaker. Next thing we're going to look at is contactors, power contactors. Okay, there's two types. There's called a latch power contact and a power contactor itself. I just want to highlight a couple of things, gentlemen, because we need to know it before the next thing. Here's my main contacts, okay? So we call these ones, these are the main contacts. And that's going to be like my A phase, B phase, C phase. And these things are what's called the auxiliary contacts, okay? The auxiliary contacts. In a basic system, what we would really want is when the main contacts are open, you can see here my auxiliary contacts would be closed, okay? This is just a simple power contactor. So that's the relationship. Our main contacts, our main power contacts are open, my auxiliary contacts will be closed, okay? And if I close my contacts, my auxiliary contacts are open. And what a contactor does, it allows us to do two things. Remotely switch on my generators, because I mean that could be carrying hundreds of amps. Okay, so really I want a small switch to turn it on and off, because I might get electrocuted. Plus the fact is that contactor might be on the wing or in the electronics compartment. And two, I need to do it remotely. Yeah, so I'm going to be able to do it remotely. And there you go. There's the switch to switch the generator on and off. Okay, so a contactor is just basically a big large relay. Okay. Now we're going to talk about something called a latched, okay, power contactor. A latched power contactor. If I look at this basic contactor right now, as soon as I switch on the coil, switch on the current, put 28 volts. It'll go through this coil and it will pull, that will produce a magnetic field and pull all these contacts to change position. So it would close these contacts and again it would open these contacts. Now, what else could have caused these contacts to open? One of the things is called G-forces. Okay, you hit a pocket of air, you get the G-force. There might be enough G-force to actually cause the contacts to open, lose your power supply. Or in faster aircraft, you do turns, you might actually have enough G-force to open it. So a latch contactor, if you think about, if you look at here, I've got a latch. So when I energize it, it comes down and physically locks, okay? It's a mechanical latch. So the first thing a latch contactor does is the power contactor which is latched is not subject to, is not affected by any G-forces. And the second thing is, to keep this type of contactor closed, I need a current to go through that coil all the time. It's only a small current, but that current comes out of a generator. That generator has to come from the engine. The engine to move needs fuel. Over one flight, does it make a bit of difference? Over a whole year, over a whole fleet, it mounts up to fuel. So what we can actually have is, it's more energy efficient to lock my contactor in. So all I need is power in a latch contactor. I only need power to change state. So I need power to energize it closed and power to open it up. So what are the two advantages of a power contactor? One, it's not subject to G-forces. And two, we only need power to change its state, to energize it or to de-energize it. Okay. These are basic relays. You're all electricians, you understand these relays, or you're all mechanics. This is basically how a relay works, okay? I'll just give a quick highlight on this one. If I put this switch down, okay, I'll get current going through this coil. That'll produce a magnetic field. And that's now going to cause those contacts to change over. Okay, and as you can see down here, I switch one thing off, put another thing on. So that's how a basic relay works, or all relays work, to be honest. Okay. Complex, I can turn things on and off. Okay, so as you said there's my latch contactor. We only need power to change state, okay? And it's not subject to G-forces, okay? The next one is something called a power contactor, okay? Just a basic power contactor, but you can see it's got a diode there. And it's to stop something called hold on or relay chatter. Sometimes relays can flicker. If I have my positive here, yeah, positive, negative. If I put my current going through the coil, it can't go through that diode because that's the negative side here. That's the negative side there, that's the positive side there. Put it through there, my contacts will change over. No problem. Now if I switch this power contactor off, what can happen is we get something called a back EMF. And the back EMF is trying to stop, okay, the relay from de-energizing. And what it'll end up doing is this coil will produce, okay, a positive. It will produce a positive here and a negative there. But because of this diode, that current will flow through the diode rather than the coil. So it's a bypass, it's a short circuit. So basically, my relays don't come down and go. They can chatter, and what we can call damage to the system. So what's the purpose of the diode across the energizing coil in a power contactor? Is to stop what they call power hold on or relay chatter. So it short circuits the current going across the coil. Right, we'll look at the two basic systems, okay? Don't worry, we don't have to go into this diagram, okay? But what we just need to understand, just to highlight again, is in a split bus system, remember the generators are never connected to the same bus bar. Okay, so there's number one and there's number two. And these bus tie relays, when the system is working correctly, will always be open. But you also have other power supplies. We will look at these later on. Something called a RAT and an APU. Okay, APU. I cannot connect my APU. Remember we talked about the hold-on relays when we talked about DC? It's the exact same thing. So again, I can never parallel my APU, my ground power, or my ram air turbine when my generators are connected to that bus bar. So that's not changed from what we talked about on DC. Okay, so that's not changed. So we still cannot parallel or connect ground power, ram air turbine, auxiliary power unit when the generators are supplying the bus bar. Now, remember we said this has an advantage, okay? It does have an advantage. So remember I said one bus bar, one generator, one bus bar. And when we, those who can remember here when we did avionics and we talked about certain systems only had to have one power supply for each system. And one of the things we looked at is something called stall warning. And remember we said stall warning, the two systems need to have independent power supplies. So in a split bus system, if I have an autopilot, or if I have two autopilots, and again, autopilots need independent power supplies. Okay, so the pilot's one will come off the essential, and the co-pilots will come off the non-essential. And in a split bus system, that works, except when one of the generators fail. When one of the generators fail, whatever autopilot, or we're going to look at something called autoland, if it fails, we could have a small break in power supplies. Remember that? Remember the disadvantage of a split bus system is you could have a small interruption in power supply. So let's look at how this is covered in an autoland operation, okay, for a split bus aircraft. Split bus does meet the requirements of independent power supplies, where a parallel, we've got the synchronizing bus bar. So let's look at what happens, okay? The generator will open, the bus tie breaker will close, and now the other generator will now also supply 200 feet. This system works normally. The failed generator contact breaker opens, it's buzzed.
Hello, N.
You are stuck.
Can everyone hear me now?
No, N, can you repeat,
Hold on.
please?
You are
Okay,
stuck.
hold on a sec.
You are broken.
Time for a break.
Can you hear me?
Now.
Yes, now. Not again. यसलाई एकछिन ब्रेक लिउँ भनौँ त टेक्स्ट गरौँ त मिस्टर यादव
Can you see that, gentlemen?
Yes, N, we can see.
Okay, that's good.
Okay.
Can everyone hear me now, gentlemen?
Yes, Mr. Ian, we can hear you.
Oh, good. Right. Good, good, good. Seems to happen about the same time each day that we lose the internet, or it goes very slow. Okay, just give it a minute and we'll let people back in. Okay, gentlemen. Okay, we'll make a start. So now we're looking at this thing called Autoland. Okay, and we said hopefully before break, is this like stall warning and autopilot? One of the regulations, it has to have independent power supply. So whatever Autoland system is supplying the co-pilot, let's call that the non-essential generator. The co-pilot, it'll be the essential loads, the essential generator. Now coming into land, okay, let's say we lose one of the generators. Let's say the pilot is flying, okay, the pilot is flying. So basically the pilot's Autoland system is being fed by the essential generator. The generator is providing all the essential loads. So as the pilot comes in, okay, he's flying the aircraft in, and let's say at 1,000 feet, his generator fails. And at 1,000 feet, what will happen is the essential generator, it's failed, its generator contact breaker will open. The bus tie breaker will close, allowing the non-essential generator to supply the pilot's Autoland system. And if it either shuts down or fails, above 200 feet, remember we said 200 feet is what we call the decision height. The pilot has time to go, right, okay, Autoland's failed. It's not great weather. I'm going to go round again. So above 200 feet, my split bus system works as it should do. Okay. Now below 200 feet, okay, below 200 feet, and my generator fails. Okay, so it's still the pilot, it's still the essential loads. 200 feet, okay, coming in an A320. 200 feet is the decision height, and to call out, a decision height is where the pilot will call out that he's going to land. Okay, and to land at 200 feet, it has to see the runway. Basically, there are a few other things, but basically, it has to see the runway. So now his generator fails at 198 feet. He must be able to see the runway. But to avoid this problem with electronics switching on and off, at 200 feet, the buzz tie breaker does not close. Does not close. Therefore, the pilot will be flying, he'll be physically flying the aircraft because the Autoland system will have cut out. Okay? He's only got another, what? At 200 feet, gentlemen, what, 10, 15 seconds to fly, if that? Those are A320, you probably know that more than me. But it won't be many seconds, definitely not minutes. His instruments will go onto battery. And we all know batteries must provide power for 30 minutes. It's only going to last seconds. So, in a split bus system, gentlemen, you need to understand what happens to my Autoland system, okay? In a split bus system, you need to know what happens to the Autoland system. Above 200 feet above the decision height, the buzz tie, if a generator fails, the buzz tie breaker will close, allowing the other generator to supply that autoland system. Below 200 feet, the buzz tie breaker does not close. The serviceable generator does not supply that autoland system, and the pilot will physically fly the aircraft for those last 10-15 seconds. Okay, so we're all happy on what happens if a generator fails in a split bus system. Above 200 feet, the system will operate as normal. Buzz tie breaker will close and it will be supplied by the functioning generator. Below 200 feet, the buzz tie breaker stays open and the pilot will physically fly the aircraft down. Are we all happy on that? Okay. Yes.
This open and close of the bus type breaker is automatic or just manual?
Automatic.
Automatic.
Yep.
Okay, what senses that this 200 height which causes the
That'll come
not
from
to close?
that'll come from your radalt. Okay. The only
Okay.
accurate measurement is from the radalt.
Okay.
Okay.
Thank you.
No problem.
Ian, what is advantage and what is disadvantage of not switching the bus tiebreaker below 200? Can you explain?
Well, basically, remember I said sometimes with electronics that in a split bus system, remember the generator contact breaker opens, then the buzz tie breaker closes. So we have that small braking power supply. For electronics, this is a lifetime. It's a long time. So my electronic system could shut down completely. It could freeze, or the worst case condition, it could basically run away and it'll accelerate it. So if he's above 200 feet and either one of those three things happen, he's not made a decision to land. It can continue to fly the aircraft, or it can make the decision to go around and come back in again. Below 200 feet, he has made that decision to land. Okay? So basically, we're only talking 10-15 seconds. At 200 feet, to go around now, you probably end up crashing the tail into the runway. So at 200 feet, we don't want things switching on and off when the pilot is physically trying to fly the aircraft. So we don't allow the power to come back onto the autoland system. For that 10-15 seconds, the pilot will physically fly the aircraft. So we don't get freezes or jumps or runaways. Okay, happy on that?
Yes. Thank you, Ian.
No problem. So we'll look at the advantages between and disadvantages of a constant frequency system, okay? But we're now looking at more on a parallel system, okay? The advantage is it can handle shocks, big power draws. We'll always have a supply of the synchronizing busbar. And if all the generators are taking an equal amount of load, the life of the generator can be increased. The next thing is the disadvantages, okay? It's complex. It really is complex. One fault in one generator can also be felt on the other two generators. If they're all going to the same bus bar, one has a fault, it could feed back up. And the one thing here, if everything comes off this synchronized bus bar, we don't have independent power supply. Don't have that independent power supply that we did in the split bus system. So we'll look at connecting generators to the same bus bar. Okay. Now remember we looked at in a split bus system. It's only one generator. So all we need to do is switch it on, and it will, as long as I have certain parameters like the right voltage, it works okay. But now if I'm going to put 3 or more generators onto one bus bar, it's got to be more complex. But basically what's called synchronizing bus bars, okay? The first thing is the voltages have to be the same. The voltages have to be the same. Because if one generator's too low, remember what we said about the rules about connecting generators to the bus bar are still the same. The generator must be greater than the bus bar it's connecting to. So we must have the right voltage. We must have the same frequency. Okay, we will be looking at the frequency later on, but what happens when the frequency becomes mismatched? Because if we don't have the frequency same, we'll end up, the bigger the frequency between different generators, we'll have more of this positive and negative effects on the output, okay? And we must get the correct phase rotation. It must be going ABC. So it must be rotate, the generator's output must be feeding or going round the same way, okay? And when I connect all 3, there must be nothing coming off it. Because as soon as I put the generators, if I've got loads on the bus bar, as soon as the first bus bar they'll start to draw, okay? And that will start to bring down the voltage of one generator. And then we're going to get all these different voltages feeding round, okay? So the big thing we need to think about is when I'm connecting or generators to a synchronizing or parallel distribution system, the 3 big things we have to think about is voltage, it must be the same. The frequency, it must be the same. And the phase rotation, it must be the same, okay? So understand what are the 3 main requirements. I know we see there's 4 there, but from the generator's point of view, the voltage coming out of the generator must be the same. The frequency of the AC coming out of the generator must be the same. And the phase rotation, the direction of the ABC, or A phase, B phase, C phase, is feeding. Okay, so happy about what the 3 things a generator must do before it connects to a synchronizing or paralleling bus bar. Okay, so let's look at this load sharing. Okay, now remember we talked about AC on Friday. We talked about 2 different types of system. Why we need 400 hertz, okay? Why we need 400 hertz is we have 3 basic electrical components: resistor, capacitor, and inductor. Resistor is not worried about frequency. So in a purely resistive load, the current will be in phase with the voltage. In a reactive load, the voltage could lead the current, or the voltage could lag the current, depending if the circuit has too much capacitors or too much inductors. So the power produced, okay, we've now got to think about, in a synchronizing system, the types of power. So we have 2 types of power. We have active power, which is the purely resistive, and that's measured in watts, okay, or kilowatts. And the reactive power, okay, is volts, amps, reactive, VAR, volts, amps, reactive. So in a purely capacitive and reductive, it will have a phase angle of 90 degrees to this here is active power is my resistors, and my reactive power is my capacitors and inductors. So we've now got two power. We've got power, okay, caused by the purely resistor load watts. We have power used by the capacitors and inductors, my volts amps reactive. But when you look at the back of a generator, it says its output is, it'll say so many VA, and that's volts amps. And we call that the apparent power. That's the power, it's the total power, or the power that the generator apparently is producing. Because we can't measure in an aircraft apparent power. We can measure the reactive power, and we can measure the resistive power. And you can see here, we can do a little bit of trigonometry, and that will give us our apparent power, okay? So we're now going to look at how we load share, because each generator is going to produce an apparent power, volts, amps, and that's going to be made up of reactive power and active power, okay? That's it there. So we need to know, and what we can tell is, just like any system, okay, if I got 3 or 4 generators, what I want is to do is the active power on each of the 3 generators to be the same. My reactive power on all 3 generators to be the same. Okay, so we're looking for an even split, okay? And on my own generator, reality is I want this to also be 50-50, an even split, okay? So it says here generators should have equal loading. So the active power on one generator should equal the active power on the second generator, should also equal the active power on a third generator. And my reactive power, again, almost equal. So in reality, gentlemen, if I have 3 generators, each generator must take, okay, if I put, so here's my 1 generator, 2 generator, number 3 generator. So I want this one to have a third, hold on a second, and a third. Yes.
Can't get you. Just voice is interrupted again.
Is it? Okay. So in reality, gentlemen, each of these active loads, so each generator will produce an active load, and each generator will produce a reactive load. And ideally, each one of those loads should equal the other. So you can see here, in reality, I should have each generator supplying 1/3 of the active power or 1/3 of the reactive power. So it should be equal. Okay, it should be equal. I'm going to come back to this in a minute. Okay. In our aircraft, older aircraft used to have a voltmeter, and it would tell you the active power being used by each phase and the reactive. And all you do is you switch this here would be a switch. Okay. And you probably find in the olden days, when you had a flight engineer, that was his job to actually adjust the active and reactive load. Those who are in glass cockpit aircraft, you go into the ECAM and ECAS system, and you will actually find on the AC page, you can actually look at active and reactive loads. We're going to look at how we keep, because remember, all each one of those generators is going on to the same synchronized bus bar. So I want each generator to provide an equal load, okay? And it's what we call load sharing. Okay, load sharing. Now, if you look here, okay, if you look at this one here, this is equal load sharing, okay? So what I can say is, as you can see here, the total amount of active power so when it's balanced, if you look here, it is 3, 3, and 3, okay? So 3 lots of active power is taken, each is taking an equal load. So now I can see here in this particular example, I have a total amount of 9 units of active power. The circuit is made up of a current transformer, and that's picking off current, and it's going to flow in this circuit, okay? Going to flow in this circuit. And we have something called a load controller, okay? And that's going to determine, that's going to modify, okay? It's going to modify the torque in my constant speed drive unit. We're going to have a little look at that in a minute. But what I can say is here, there is no difference between power between here and here and here and round to this side here. So it's all equally balanced. So now let's look what happens when one of my generators provides too much active power. So you can see here number 1, it's now providing 5 units. But here, look, 2 and 2. So the total amount of power that the system can produce can't exceed 9. So it's got a maximum power the whole system can produce. If number 1, okay, has too much power, would you agree, gentlemen, I need to reduce the power coming out of that generator? Would you agree with that? Yes? Yeah.
Yes, yes.
Yes, yes, thank you. And would you agree that number 2 and number 3 generator, I need to get the power they produce up? Agree with that? Yeah. So what we actually do is, I'm going to show you, I've got a picture somewhere. There we go. Remember when we talked about the constant speed drive unit, and I said about this magnetic trim that would come from the voltage regulator. Okay, so this load controller, okay, the input for this magnetic trim comes from the load controller. And this is the bit that will actually modify, either increase or decrease the torque in the constant speed drive unit. So we now know where that magnetic trim gets its. So now let's have a look at it. If this number 1 is producing too much power, I need to reduce the power. So therefore I'm going to slow down or underdrive the constant speed drive unit. So too much power, I'm going to use the magnetic trim to underdrive the constant speed drive unit. In the 2 generators where the power, the active power was low, I'm going to speed up or overdrive the constant speed drive unit. Okay, so what have we learned about the active load sharing system? It's monitored by current transformers on the phase. My active power, each generator should be able to take a equal load, or in this case, 1/3. If an active load sharing loop, if one of the generators in the active load sharing loop produces too much power, my constant is sensed by the load controller, and the load controller will adjust the magnetic trim in the constant speed drive unit to slow it down, or what the word we use is underdrive. If one of the phases has too little power, the load controller again senses it and will cause the magnetic trim to overdrive or increase the speed, or increase the torque, of the constant speed drive unit. So you're happy on the basic operation of the active load sharing loop. It's all sensed by this load controller. Okay, good.
Yes.
Right. Now I said the total system has 9 units of power. Yep. So 5, 2, 4, and 2. What happens if one of the generators is shut down? Okay. What happens? So let's say number 3 generator has shut down. This load controller is still looking, oh, I've got nothing. I'm not taking any load. And what it's going to try and do is send this a signal to the magnetic trim to speed it up, get it to overdrive. But if the generator's failed, can I ever get this back up to 3 units? No, it can't. So this is where these little contacts come in. These are the auxiliary contacts. Oh, these are the auxiliary contacts. These are the auxiliary. Come on, give me a pen. These are the auxiliary contacts in my generator contact breaker. And we now know when the main contacts are closed, the auxiliary contacts are open, just like here. But now when the generator fails, we take the generator offline, we open up the main contacts, the generator contact breaker, and we close the auxiliary contacts. So now, any output in this loop will not go through this load controller. It will short circuit straight through these contacts. And what these auxiliary contacts do, it makes the failed generator system invisible. So the system is no longer looking for 9, it's looking for a total of 6. Because it doesn't matter. If the generator fails, we'll never get it back up to take its equal amount of power. So what happens in an active load sharing network when a generator fails? The auxiliary contacts will close, shorting out the load controller, making it invisible. Okay? Or what is the purpose of the auxiliary contacts in the active load sharing loop? It's basically, if a generator fails, it makes that generator loop invisible, and we don't worry about it anymore. Okay? So what we need to take out of this is, in an active load sharing loop, that is measuring the power used by the resistive components. It's measured by a current transformer coming off the power cables. Any difference in power is sensed by a load controller, and that load controller will modify the torque in my constant speed drive unit by the magnetic trim. If one generator takes too much power, my load controller will cause the constant speed drive unit to reduce speed or underdrive. A load controller senses too much active power, it will reduce or send it into underdrive. And what is the purpose of the auxiliary contacts? In the event of a generator failure, it will short out that load controller, making that failed generator invisible. Okay, are we all happy on the active or the resistive load sharing loop? All good?
Yeah, Ian.
Good, lovely.
Yes.
Thank you. Next thing we're going to look at is the reactive. So this is the bit for the capacitive. And inductive, okay? The sensor this time is something called a mutual reactor, okay? If you actually look at it, gents, the system looks very, very similar. So let's have a look. Again, my reactive load, when it's balanced, it should, if you can see here, it should equally share the amount of reactive power when it's all equal or balanced. And this thing here, okay, oops, when I find it, this here is a mutual reactor. What is a mutual reactor? Okay, I know you've got a diagram in your book. It's quite complex in how it works. But if I was to say that was the primary and that was the secondary coil of a transformer, okay? So just think about it as it's a very complex transformer. It has a lots of phase angle shifts in this. It's quite complex. And we don't need to go into that complexity on this course. So the sensor is a mutual reactor. And this mutual reactor is going to my voltage regulator. And what it's going to do is going to artificially tell the voltage regulator that the voltage is too high or the voltage is too low. And it will actually reduce the power, okay? It will actually reduce the power by reducing the voltage. The current will stay the same, but the voltage will go up. So I can see here, if I know it's a different formula, but if I was just use the basic formula P equals P equals IV, if the current goes up, I need to bring the voltage down. If the current goes down, I need to bring the voltage up. And this is what this feed to the voltage regulator is going to do. As you can see, it's very, very similar. Okay, the reactive loop is very, very similar. There's my current transformer. There's my auxiliary contacts. But instead of a mutual reactor, okay, sorry, instead of a load controller, I have a mutual reactor. So let's look what happens, okay? Let's look what happens. So this one here, generator 1, basically is taking too much reactive power. If you can see here now, there's a feed from the cable, and that's going to my voltage regulator. If I start to take too much power, I start to take too much power, or in this case, I start to draw too much current, So power, I'm going to keep at the moment, my voltage is the same, but the current goes up. So my power has gone up. So to get this down, I need to get my voltage regulator to provide less excitation. So how it works. So even if I have here, right now I have 115 volts on phase A. That means I have 115 volts here. But if you look where the primary side of the mutual reactor is, it's coming off that current transformer. As I said, it's a very complex transformer, but if the current goes up, we're going to change that current into voltage. So if the current goes up, the voltage goes up. And if that's just like a normal transformer, if the voltage goes up on one side, the voltage will go up on the other side. So let's say it increases here by, in the primary coil of the mutual reactor, it goes up by 2 volts. I've got 115 in. I have 2 volts on that secondary. I now have, going to my voltage regulator, 117. My voltage regulator goes, my voltage for my generator has gone up by 2 volts. So therefore, I'm going to reduce the excitation. So you can see here, look, if the power went up because of the current, the voltage goes down, and that's what the voltage regulator is going to do. So in a reactive power sharing network, it is sensed by a mutual reactor. And what does a mutual reactor do? It artificially sends a voltage to my voltage regulator, which will reduce the excitation voltage. So what is affected by, or what controls reactive power? It is the mutual reactor, which artificially increases or decreases the voltage produced by my voltage regulator to my excitation coil. And again, here, look, my auxiliary contacts. If the generator fails, they will close. Oops, they will close, shorting out the mutual reactor, therefore making it invisible. Are we happy on reactive load sharing? Yep. It's done by a mutual reactor, which will change the excitation from my voltage regulator. Reactive power goes up. I need to get the voltage regulator excitation down. Are we all happy in the operation of the reactive load sharing loop?
Hello, Ian.
Yes.
That formula, power is equal to I and IV. Yes.
Yeah. That's the DC one. That's the DC. I know there's an AC one, but this, you can see the relationship. Okay. Yes, Pakesh.
The current in this, which is taking 5 units of load.
Yep.
The current is high.
Yes, that's correct. The current goes up, therefore my reactive power goes up.
Current is high. Voltage is also high, I think.
It is, but okay. Let's have a quick look at Pakesh. Let's have a look. Let's get my pad. So let's say here on number 1. Okay. We're going to use an easy figure. So P equals IV, and I know this is the DC value. I know when we talk about AC, we've got to put other things in, but just look at the basics of this. Okay, so if I have 10 amps and I have 115, okay, I'm going to have 1,150 watts. Or sorry, VAR. Sorry, VAR. Yep, agree with that.
Okay.
Yep. So now, okay, let's say I still need that total. I need to get this down. So now if the current goes up, let's say now the current goes up to 20. Okay. I still need, so what's going to happen is I need to reduce the power, okay, the voltage by half. In this case, it'll be 50, all right, I'll work this out, 160. 67.5, 20 times that will still give me 1.5. So I'm actually going to try and reduce it by reducing the voltage.
Okay.
So power goes up in the reactive circuit, power goes up because it takes too much current. Therefore, I'll need to reduce the voltage. Now we're talking, Prakesh, 1 or 2 volts to get the power equal. We're not talking 75 volts, but it's only 1 or 2 volts. So when the current goes up, we bring it down. This whole circuit is constant. All 3 these circuits will be constantly changing all the time.
Okay.
Yep.
Thank you. Yep.
So load sharing only takes place when we are paralleling, i.e. putting them onto a synchronized bus bar. When not, it says there, the bus tie breaker or the generator contact breaker auxiliary contacts will close and we short out the sensor. And that's the same when it's reactive or active load. So just to highlight, active load is a load controller, and that will modify the torque in the constant speed drive unit. Reactive load is measured by a mutual reactor, which will modify the voltage or the excitation voltage by the voltage regulator. And what's the purpose of the auxiliary contacts? When a generator fails, it shorts it out, making it invisible. We're now going to look at some faults in the system, okay? We're now going to look at some faults in these systems, okay? So let's have a quick look. Oh, wrong slide. Right, we're now going to look at some of these extra AC specific faults. Over excitation, over voltage, under excitation, under voltage, differential protection, instability protection, negative voltage sequence, over frequency, and under frequency. Okay, we will be looking at all these different systems. Just have a quick look. Here we go. This is my synchronizing bus bar. Okay, here's my synchronizing bus bar. And there's my number 1 generator, number 2 generator, number 3 generator. And hopefully each one of them is producing 115 and equal active and equal, sorry, and my reactive loads are equal. In a normal configuration, in a parallel distribution system, when it's fully operational, the generator contact breaker, the GCB, and the bus tie breaker are normally closed. Okay, we're just going to give an example here. One of the generators, its output drops to 20 volts. There you go. You can see now it must be the number 1. What we're going to do is open the GCB. Yep. Well, because it's that low, we can actually, we'll open up the bus tie breaker if we require. So we can still see here, we're still supplying the loads that are coming off the synchronizing bus bar. So we're going to look at the different faults, okay? Can we just take a quick 5-minute break, gents? Okay, 5 minutes, we'll be back in and we'll try and get this finished off. Okay, because I need to go to the toilet, I'm afraid. Excuse me. 5 minutes.
Okay, sir.
Oh, that's better. Right, we all ready to go in, gentlemen?
All ready?
Good. So the first fault we're going to talk about. Is there something I want to get back in? The first fault. Come on. The first fault we're going to talk about is overexcitation. Okay. Too much excitation voltage. And it's usually caused by a fault in the voltage regulator. Okay. In which, right, and if I get too much excitation, I'm going to produce too much reactive power. Okay, so it's usually caused by an incorrect or something wrong with the voltage regulator. Okay, because what will happen is if I overexcite it, not only is the current going to go up, the voltage is going to go up, okay? So it's usually something to do with the reactive, could be something to do with the reactive load sharing loop, but it's the fault still goes to the voltage regulator, okay? So overexcitation, the generator will take more of that reactive load. And what the system first does is it opens the buzz tie breaker, okay? It takes it off the synchronizing buzz bar. And if I take it off the synchronizing buzz bar, as long as other things don't go wrong, okay, it can still supply its own individual buzz bar, but it can't provide power to the synchronizing buzz bar. So in overexcitation, the generators take more of that reactive load. It'll open the buzz tie breaker, and it's usually caused by the voltage regulator, okay, or something to do with the load sharing loop, but usually it's the voltage regulator that's gone wrong, okay. So that's that's the first fault, overexcitation, usually caused by the voltage regulator, okay. And if it says there, if we're tripping or opening the buzz tie breaker, the fault clears, it is the load sharing loop rather than the voltage regulator. Again, under excitation, if you look at it, what's the difference? It's voltage, it's caused by a voltage regulator and the load sharing loop. So anything to do with excitation has to be the voltage regulator or the load sharing loop. So when you're given, if you're asked a question about what's a possible cause of over or under excitation in a parallel distribution system, it's either voltage regulator or load sharing loop, okay? Usually voltage regulator. The load sharing loop's very, 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 having talked to guys who worked on 4-engine aircraft, it very, 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 very rarely goes wrong, okay? Over voltage, okay? We've looked at over voltage already. We looked at a DC, okay? So we've got volts exceeding what we want to be, okay? So we'll come back to this the longer it's taken offline. So to reduce, just like in the DC, we had the overvolts latch relay, which removed the generator field. Okay, so we're going to trip or open the generator field relay. And remember, gentlemen, what did I say also happens when we remove the generator excitation field? What else also happens at the same time? Can you remember?
Line connector disconnect.
Yes, exactly. We open the generator contact breaker. Those two, whether it's AC or DC, are exactly the same. Okay, we remove it. Okay, we remove it, open the field, remove it from the distribution system. So open up the generator field relay, we open up the generator contact breaker. And again, normally caused by the voltage regulator. But this thing in line 2, the higher the voltage, the longer the generator is taken offline. Okay. If I have a high voltage, if I have a high voltage, let's say it's 117 volts. Yeah. Regulator will deal with that, bring it down. But as that voltage goes up, things are going to start to heat up, okay? So that's why we have this. The higher the voltage, the longer the generator is to allow the systems to cool down, okay? So over voltage, we remove the generator field and we take the generator offline. Under voltage, guess what? We take the generator field away and we remove the generator contact breaker. So again, voltage, it's the exact same. We remove, so an over or under voltage condition, we remove the generator field and we take the generator offline by opening up the generator contact breaker. And both will be caused by some sort of voltage regulator fault. Differential protection, we've done this before. Current going into the circuit. So current coming into the circuit from the generator must equal the current going out. If the two are not the same, okay, we'll actually remove the generator from the distribution circuit, and again, if we're removing it from it, we remove the excitation field. The next one, this is probably slightly new to you. It's called instability protection. Now remember that diagram we looked at, three generators going onto the same synchronizing bus bar. And we said to parallel or connect generators to a synchronizing bus bar with several things. We had to make sure we had the correct voltage. We had to have the same frequency, and the generators had to rotate. The output had to be what we call correct phase rotation. If we don't have the frequency correct, we'll actually get this instability, okay? This instability will get positive and negative, okay? We'll get output might go up and my output might go down. So I want to go back to this little diagram here, okay? Everything's working correctly. Everything is working correctly. All three generators are producing 115 volts. And what was the frequency of my AC? Anyone? It was 400 hertz.
400 hertz.
Yes. So on my synchronizing bus bar, I want 115, 400 hertz. And I want the output of each of the generators to be what we call synchronized. So basically, all three of the waveforms will start at exactly the same place. And I want all three of the waveforms to have 400 hertz. But let's say now one has 410 hertz frequency. You can see what's happening now. We're going to get the voltage. At one point, we're going to get too much voltage, and at one point, we're going to get too little. But let's say now we are measuring 410 hertz on the synchronizing bus bar. So basic means one of these generators must be producing a frequency of 410 hertz. Going back to the old days, we used to have a flight engineer. What the flight engineer would do would be, looking at his gauges, he would individually open up the bus tie breaker on each generator. Okay, so he'd open up this one. If the fault was still there, it wasn't number 3 generator. If we opened up this one, so closed number 3, opened up number 2, the fault was still there. It would close number 2, and if we opened up number 1 and the fault cleared, he would know that what generator was causing this instability was the number 1 generator. Again, this is all done computerized now. It's all done by the computer. So that's what instability protection is. Oops. So instability protection detects oscillation between the generators. Okay, and what it says here, it is allowed an 8 Hertz difference. Okay, please remember that generator. So instability protection, if one of the generators, its output is greater by 8 Hertz, it will open up the buzz tie breaker. Yeah, so the system will know which generator is causing the fault. Okay, if it's that bad, we can. So initially, to determine which generator's producing that instability protection, we will open up the buzz tie breaker, and that will tell us which one is causing it. And when we know which one's causing it, we will trip the generator field relay. And if we trip the generator field relay, what else trips? Come on.
GCB.
GCB, yeah, correct. The GCB will also trip. And it could be caused by anything. To be honest, it could be caused by anything. It could be the constant speed drive unit, or the voltage regulator, or the generator itself. Okay. So what is instability protection, or what is frequency instability? It is anything greater than 8 Hertz between the generators. How do we diagnose that fault? We'll open up in sequence the buzz tie breakers for each generator. If the fault clears when we open up that buzz tie breaker, we know what generator has got the problem. We can take it offline by removing the excitation field and taking it offline by tripping the GCB. The next thing is something called negative sequence. Okay, negative sequence. Remember we talked about the differential protection device in generators, and that basically stopped output from the buzz tie breaker back to the generator. Well, a negative sequence is the same, but it's actually on the distribution side. Okay, it's actually stopping things coming from the system back into the buzz bar. Okay, and what we do is we basically isolate the buzz tie breakers. Okay, so that's what negative sequence is. It's a fault on the distribution side. Okay, so it's basically differential, but on the differential protection, but on the distribution side. Next thing we're going to look at is something called over frequency. Okay, and remember, gentlemen, when we talked about the constant speed drive unit or the variable speed constant frequency, one of the things we talked about was the oil level. So in a constant speed drive unit, if the oil level is incorrect, it won't work correctly, and therefore the frequency of my generator is going to be not correct. So if you were asked what could be a cause of incorrect, now it could be over or under frequency, it doesn't matter. What could cause over or under frequency in a generator, it's normally caused by incorrect oil level in the constant speed drive unit. Lost me arrow. Here we go. Okay. And the one thing we've got to remember is over frequency. We now know what causes it. We want to know you now need to know what will happen if the output of my generator, the frequency goes too high. It will damage capacitive loads. Why will it damage capacitive loads? If you can remember, go back to mod 3, capacitors like higher frequencies. The higher the frequency, the more current that can flow in a capacitive circuit. If I put lots of current in, I'll end up burning things out. Okay, so over frequency, what causes it? It is low oil level in a constant speed drive unit. What will over frequency do? It will damage systems or loads that are mainly capacitive. Okay, so what happens if we see this? It will be, guess what? We'll trip the generator field relay, and guess what? If we trip the generator field relay, we generate the contact breaker. Yes, well done.
Bus tie breaker is
And the other thing is, we'll put the constant speed drive unit into underdrive, but just be aware. What normally causes over frequency? It is the oil level in the constant speed drive unit. What types of load will over frequency damage? It will damage capacitive. Okay. And again, what we're going to do, we're going to take it offline. Under frequency, okay? Under frequency. If the generator's not producing high enough frequency, it says there we're going to damage inductive loads, okay? If you remember back to mod 3, inductive loads like low frequencies, okay? So the lower the frequency, and an inductive circuit will get more current, which will cause damage. So in an under frequency condition, what loads will be damaged? It's going to be inductive loads. But here's the next bit. It doesn't operate during engine shutdown. So when the pilot retards the throttles, brings the throttles back to shut the engine down, there's a little circuit made. Okay, it completes a little circuit to tell the generator control unit, the GCU, that the engine is shutting down, so we don't have to worry about the under frequency circuit, because basically it'll start getting all these warnings flashing, and it's going to be, it's not a fault because the engine is shutting down, the frequency of the turbine is slowing down. Okay, the generator will also slow down. So when does the under frequency circuit in a fixed wing aircraft, okay, be invalid? Is when the engine is shutting down. Now, don't worry, gentlemen, okay, you're not going to be asked to remember any times, okay? Don't worry about that. And again, that would probably change very slightly between aircraft. And I tell you one, gentlemen, if you could remember each one of those times for each one of those different faults, you're a better man than me, okay? But the two I want to look about is over voltage, okay? Over voltage. And it says there, it doesn't give a time, it says inverse time delay. Inverse time delay. What that means is, The higher, the larger my over voltage, the smaller the time I have to shut it down. Because if I've got a high voltage, it could produce a high current. That both these high voltages and high currents could quite quickly damage circuits. So when I have a very, very high voltage, I have a short time. So my voltage goes from 115 to 170. And it's done it very, very fast. I have a short time to take it offline so it doesn't cause damage. So you need to understand what's the relationship between an over voltage condition and we take the generator offline. It's inversely proportional. So if I have a quick high output, I have a small time to take it off. But as I have a small over voltage and it goes slowly, remember my excitation system is trying to control the output voltage. So if it goes 115, 116, 117, 118, 119, 120, 125, we're allowing time for the system to try and get the voltage down. So if it's a slow, okay, or a small increase of over voltage, I have a long time before I need to take it offline. So please remember that, okay? And then it talks about the fire handle. When I pull the engine, okay, I pull the engine fire handle. There's a lot of things that when you do that, it's not just basically getting the fire bottle. It says it takes half a second for it to trip. Why half a second? Don't know why they say half a second, but remember my generator might have times to shut things down, okay? I might need electricity to shut certain things down. So we don't just pull it and automatically. Things will automatically happen when you pull the T handle or the fire handle in an engine. So that half a second, we still provide power for other things to happen in the aircraft or round the engine before we remove the electrical supply, okay? That's it there, but basically I want you to concentrate on the over voltage condition. Next thing we're going to look at, gentlemen, is an APU, auxiliary power unit. Okay, auxiliary power unit. Now, the gentlemen here who work on the A320, okay, are going to start shouting at me in a moment, okay? Because what we say in our notes, it's the same generator that's on the main. It's the main generator on the engines. But those who are working, okay, those who are working on the A320, will you confirm that the generator that's on the APU is not the exact same generator that is on the main engine? Can you confirm that for me, please?
Yes, we have different.
You have different, yes, you do. Okay. They used to have the same generator on the engine as it is on the APU. Okay, I'm in the process of getting the notes changed on that. But what will happen is the generator that's on the APU will provide the same power as the engine on the generator on the main engine. Okay. So it will provide the same power. So if one generator fails, we can actually connect the auxiliary power unit to the bus bar of the failed engine. Okay. There's a problem with that. Okay. There's a problem that we'll look at that in a second. My APU, okay? My APU is a small gas turbine, usually down the back of the aircraft, usually under the fin somewhere. And the APU, unlike the engines, okay, where you can move the throttle, an APU, it will run up to 1 RPM, okay? The APU will run up to one specific RPM and it won't change. So therefore, at the back of my APU, I can put my generator without a constant speed drive unit or a variable speed constant frequency type generator, because the rotation from my APU gearbox is constant. So therefore, the RPM of the armature in my generator is constant. Therefore, the frequency is constant. So that's the first good thing. My APU, my generator, doesn't need a constant speed drive unit. The downside is I cannot connect that APU. If I've got a parallel system, okay, so more than 3 engines, 3 or more engines going to synchronizing busbar, I can't synchronize it with other generators. So I cannot connect it to the synchronizing busbar. I only can connect it to its own individual busbar. Therefore, I cannot parallel my generator from my APU to my synchronizing busbar. And most of you will know the APU doesn't just provide, hasn't just got a connection for a generator, it's got connection for hydraulic pumps, pneumatic pumps. And you might actually find there is only a hydraulic pump, and that feeds off to a hydraulically run generator and a hydraulically run pneumatic pump. Is that what you've got on the A320? Is this a hydraulic unit which feeds the pneumatics and the generator? Is that correct on a 320? Or have you got 3 units attached to the APU?
Yes, yes.
Which one is it?
It's pneumatic.
So yeah, okay. So comes off. So that's an APU. So what does the generator that's attached to an APU? What doesn't it need? It doesn't need a constant speed drive unit. Why? Because the APU runs at a constant RPM. That's the things to remember that. Okay. Generator, it cannot be paralleled. And it runs at a constant RPM. The APU runs at a constant RPM, so we don't need a constant speed drive unit. Next thing, we've got something called a Ramier turbine. Okay. So you lose both generators. This is going to deploy, okay? It's going to deploy. Or you lose 2 generators, you lose your generator from your APU. This is the last thing it deploys. It's a Ramier turbine. It's a little windmill, okay? Little windmill. At the back, it might be an hydraulic pump to run pneumatics and a generator. This is very limited amount of power. The AC won't be providing power to everything. Okay, so that's what our Ramier. Basically, when everything else has failed, we can deploy this and we'll get certain power. But now let's have a look at this. It's a massive big lump, okay? They're quite heavy, okay? And they're not very aerodynamic because we need it not to be aerodynamic for my propeller to turn. And that's good. If I'm up at 30,000 feet, I lose my generators, deploy the RAT, it gives me AC. And at 600 knots, it doesn't make a difference. Now when I start to land, okay, I start to slow down. Two things happen. I haven't got enough wind across my ram air turbine, therefore the output will go down and basically will actually lose the output. And the second is, it will cause a drag on the aircraft at lower speeds. Now, if I've gone from 30,000 feet to try and land at a runway, it's done its job. I'm quite happy it's produced a bit of drag. But let's say I'm now coming into land. Okay, coming into land, fly into a flock of geese. I lose both engines and I lose my both generators. I don't have any power. Okay, I don't have any engines either. So if I was to deploy the ram air turbine in this sort of situation, it's creating a massive drag. Okay, so I won't be able to glide is better. So what happens, a ram air turbine, if the aircraft is below certain speeds, okay, and that will depend on the aircraft, it will not deploy when you have a generator failure, and the battery via the inverter will provide my AC loads. Okay, so basically my battery provides the ultimate power. So what do I know about the ram air turbine? What it is a little windmill. It's going to power a little generator, hydraulics, etc. It will only deploy when the aircraft is above a set speed. And again, that will be different between every single aircraft. And if the RAT doesn't deploy, the batteries will power an inverter to give AC to my aircraft. Okay. Unfortunately, gentlemen, helicopters, we don't have a ram air turbine. Okay. As it says there, drives a hydraulic pump which has, if it's in a system which has a hydraulic driven generator or a direct drive. Okay, we're now going to look at putting ground power onto aircraft. Okay, looking at ground power onto aircraft. And depend where you are in the world, depend what your ground power units are. Okay, there's your mobile one, the big grey one. You either tow by a tractor. You've got preset mobile ones. Preset fixed ground power units, and we have these ground power units, which actually you fold it down when you're not using it. I can't remember what I think is it mobile units you've got at Kathmandu Airport? The mobile ground power units.
Yes.
Yes,
Yeah.
sir.
Yeah, I couldn't remember seeing the yellow ones. These
Yeah,
ones
we don't
here.
have fixed.
Yeah, I didn't think so. I couldn't remember any. There's the one here. This one here. How they all work the same. They'll be either AC or DC generators. Okay. Fixed mobile. Need to either usually drag it by a tractor or a tug. These ones here, the ones that are actually underground, we don't tend to find them much in Europe, okay? Because it rains a lot in Europe and these would tend to get filled up with water. So we either have fixed or mobile. These are quite common in very dry areas, dry countries, but these either mobile or fixed are the two main ways we provide power. Okay, so we're going to look at application of, basically it says to a light aircraft, and you can see here, gentlemen, it is the 3-pin DC plug. Okay, 3 pins. The two big pins, one's a neutral, 1 to 28 volts, and the small pin is the 28 for the hold-off circuit. Remember that? So we can not allowed paralleling of power, so we can't produce the generators onto the bus bar when I've got ground power applied. So before putting it on, okay, check the voltage and the polarity of the ground supply. Check that the external plug is clean, dry, and undamaged. Okay, clean, all right, it's covered in oil, get your hands dirty. Dry, if there's water and you put it on, electricity might want to go down that. Okay, so it's a safety thing for you as well as the aircraft and the ground power. If it's been lying in water, clean it or get another power unit with a clean plug. If it's damaged, like something's went over it, inside this plug, the 3 pins, the insulation, the rubber around the 3 pins might have broken. And as soon as I put in power, I might end up with a short circuit. So before you fit the plug, make sure it's clean, dry, and undamaged. Okay. When we're putting DC on, check that the external power and the aircraft battery master switch are off. Connect to external power and make sure the plug is fully home. Why do we make sure the plug is fully home or fully in? It's for this small plug to mate or connect with the small pin in the external plug. So we get that hold off relay made. We switch on the external supply and then the aircraft battery switch and carry out whatever we need to do. And then we disconnect the external supply by switching off the battery master switch, then setting off the external supply. And then we basically put everything away. Okay, and then you can connect use the aircraft as you want. It says there, and if the aircraft electrical system is to be used again after engine starting, we put the battery master switch on. Now, I'll also mention somewhere in your notes, gentlemen, these are general rules. Your aircraft will be slightly different. Okay, there will be slightly differences about how you specifically how you put things, but things are going to be correct. Is it the correct voltage supply? Is the socket clean, dry, and undamaged? Before we put the plug into the aircraft, the ground power unit is off, and we make sure we push it fully in. Those 3 things don't change between aircraft. Okay. So just be aware of that. Okay. Those things definitely do not change between aircraft. But what we would say in a general sense, we then say put the supply on. Once you've got the supply on, you can put the batteries on. And when you disconnect, okay, switch off the battery, then switch off the supply. So that's connecting power to the light or DC aircraft. Now we're looking to put power on a large aircraft, okay? And those who are on the A320, you'll recognise something similar. I think this is the power socket off a 737. Okay. Again, check that this external supply is capacible, okay? And remember this, when you look at it, we look for the correct voltage, the correct frequency, and the phase rotation, and that the power supply is switched off. Okay, so always remember that. What you're going to check, the power supply before connecting to a large aircraft is the voltage is correct, the frequency is correct, and the phase rotation is also correct. Again, this hasn't changed. Check that the plug is clean, dry, and undamaged. Yep. No water, so we're not going to take an electric shock. And it's undamaged. Nothing's rolled over it. Connect the external socket, making sure it's fully home, fully mated, before we switch on the external power supply. Then when we put the power on, in the aircraft, we check the voltage and the frequency of the supply is correct in accordance with the aircraft maintenance manual. If it's not, shut it down. Okay, and then we disconnect from the aircraft, okay, and put everything away correctly. So you can see here, gentlemen, whether it's AC or DC, the basics of, is it the correct power unit, correct voltage? If it's AC, correct frequency and correct phase rotation. Both light aircraft and large aircraft, is the power socket clean, damaged, and not been left in the wet? Is it been put in correctly? Okay, is it been put in correctly? With large aircraft, somebody should be in the cockpit looking at the power, or either in the voltmeter or the power page of the ECAM or ECAS system, making sure that it's the correct voltage and it's the correct frequency coming onto the aircraft. And then when you finish, switch everything off. Okay, switch everything off. And here's our 6-pin connector. Okay, here's our 6-pin connector. A, B, and C, there's our 3 phases, and there's my neutral. No difference from a generator. A phase, B phase, C phase. E and F pins is 28 volts DC. That will go to some sort of hold-off relay or ground power relay. We don't need to know where. But what you do need to know, gentlemen, is in a 6-pin AC external connector, what is being provided? 3 phases, A, B, and C, and a neutral, and 2 28-volt DC supplies. Are we all happy on connecting ground power? Yep.
Yes, sir.
Does anyone want to go through anything we have done this morning? Anyone? Have a read through the notes, especially the reactive and active power sharing, but just listen to what are a lot of complex words in there. In reactive load sharing, it is a mutual reactor which goes to my voltage regulator. Active power is a load controller, and that regulates the constant speed drive unit by the magnetic trim. If a generator fails, either the load controller or the mutual reactor is shorted out by the auxiliary contacts. And in an aircraft, each generator should take equal amounts of active power and equal amounts of reactive power. Okay. Tomorrow, gentlemen. Okay, what's going to happen now is I have finished with the Mod 11 students for today. Okay, I have finished with the Mod students for today. We're going to come back tomorrow and we'll all be together. We'll all come back together to do the lighting module. Lighting is easy. It's all level 1 questions. Okay, and most of you know a lot about lighting already. This afternoon, gentlemen, when we come back at 1 o'clock, oh, come back in an hour, it will be, I'll need the B2s and the 1.3 students to go through helicopter. Okay, we're just going to be looking at the differences, the components, the main differences between large helicopter power operation and fixed wing power operation. Okay, so how many people am I getting coming back this afternoon? You put your hands up, please, gents. Oh, lots of yous. Okay, good. Okay, right, gentlemen. We'll come back in an hour. So my 1.3 and B2s will come back in an hour. 1.1s, okay. That's me finished with you today, unless you want to hear about helicopters. Does any of the fixed wing people want to know about helicopters? Didn't think so. Okay. Def, you say something? No?
No.
No? Okay. Right, gentlemen, so we'll go 1.1 people. Have a nice day. 1.3 and B2 people, I will see you in 1 hour's time. Have a read through the notes, and again, tomorrow morning we will go through any questions that you have. Okay? So I will see the 1.1s tomorrow, and the B2s and the 1.3s I will see in 1 hour's time. After I have my lunch.
Yeah.
Yes? Yes? Yes?
If we like, we can stay, no? 1.1?
If you want. It's entirely up to you if you want to listen, but none of these questions will be in your exam.
Okay. We can listen for our interest.
You can listen for interest, okay? You can listen for interest, or you can revise. It's entirely up to you. Okay? If you any of the 1.1 people want to come back, you're more than happy. Okay?
Okay, thank you.
Right. So I will see you in 1 hour's time.
$16.45.